What's up, guys? It's Mr. Gaines here again with another Algebra 2 instructional video as we continue our discussion on the analytic parabola. Last time we took a look at a way, a method that we could come up with a standard equation for an analytic parabola given information about the focus, directrix, or vertex, two of those three things. And it was through the method of deriving the equation. It took us a little while. There's a lot of work in there, a lot of opportunity to make mistakes, but we did get to the standard version of an equation. Now, what we can do is also a separative method for finding an equation. This is going to be a lot shorter and a lot less complicated. So problem number 3, it says for each of the following, use any method to find an equation for a parabola matching the criteria. So instead of going from the definition of an analytic parabola, what we're going to do is we're going to approach this problem with an idea of the equation. So if we can remember a vertical parabola has the equation y equals 1 over 4d times the quantity x minus h squared plus k. This will allow us to create an equation with a lot less work. So let's go ahead and take a look at 3a. So what I've done here is I've gone ahead and I've sketched out a visual. Now, this is also the last problem that we took a look at in the notes, where we actually derived the standard equation using the other method. Now we're going to look at it approaching it from the vertex form of a parabola. So what I can do here is essentially all I need to do is find out the missing pieces of information and substitute into this equation. So I need to know the vertex to get my h and my k, and I need to know the value d. So let's start with the value d. Remember, the value d is the distance from the vertex to the focus, which is also the same as the distance from the directrix to the focus. Or sorry, from the directrix to the vertex. You can physically count this distance. You could use the distance formula, but it's a lot easier. We know that the vertex is at -2, 4, and the focus is at -2, 1, so the distance in between these has to be 3. So I'm going to go into that equation, and I'm going to substitute in 3 for d. Now, one thing that I also want to make sure that I take care of here is that this parabola opens down. This is a downward facing parabola, meaning that it's been reflected. So I need to put a negative in front of this equation to represent that reflection. Now, I can continue to substitute. X minus h. Well, remember, h is the x value of my vertex. So x minus -2 quantity squared plus k. Remember, k is the y value of my vertex. And so here I can substitute each of the pieces, and now I can simplify. -1/12 times x plus 2 quantity squared plus 4. And there I don't have the standard equation, but I have the vertex equation for this parabola. Now, let me go ahead and go back to my calculator where I have the last graph in that we had from the previous one. We found the standard equation. Let me go ahead and type in the vertex equation. So typing in what we see here as the equation that we just found, and I'm going to graph them both. And I'm going to notice no change to my graph. I'm going to go ahead and take a look at my table and notice that each x value has the same y value. These two functions are the same. It's a different way to write the same function. So what we can see is if we're told that we have to derive the standard equation, it's going to take a lot of work. We did that in the last video. There's a use of the distance formula in the definition, some simplifying, a lot of algebraic steps. If we're not told that we have to find the standard form deriving the equation, we can go here and we can substitute into the vertex form with the different pieces that we know, and then we have the equation in a much more simple manner. So unless you're told you have to derive the equation, use the vertex form for a parabola and substitute into that value. Let's go ahead and take a look at B. I've drawn out a sketch for B. a focus at 7, -3, and a directrix at y equals -7. So I know this parabola opens up because my focus is above my directrix. So the vertex happens somewhere in between those two, and the parabola has to open around that focus. So it's going to be an upward facing parabola here. Now, if I want to substitute into my equation, I need to know my vertex, and I need to know the distance from my focus to my vertex. I don't know either of those two things, but I can find both. What I know here is the distance from my focus all the way down here to my directrix. I can find that. So if my focus is at 7, -3, and my directrix is at y equals -7, there's 4 units in between these. Now, let's not get confused. This is not the value for D. Remember, the value for D is equal to the distance from the focus to the vertex or the vertex to the directrix, not the focus to the directrix. But the distance from focus to vertex and from vertex to directrix is the same. So D has to be 1/2 the distance from the focus to the directrix. So D is 2. So if I want to substitute into my equation, I can start that substitution. I know this is 1/4 times 2. This is going to be a positive leading coefficient because it opens up. Now, what I don't know is my vertex point here. But let's go back to things that we do know. We do know that the vertex lies on the axis of symmetry. So the vertex and the focus both lie on the same axis of symmetry, which is going to have an x value of 7. That x value is given to us in the focus. The y value we can find by using our distance d. The y value, or d, it gives us the distance from focus to vertex or from directrix to vertex. So the vertex has to be 2 units above the directrix and also 2 units below the focus. So it's going to be at 7, -5. So now I can substitute in my 7 for my h, my -5 for my k. Simplifying this equation, I get 1/8 times x minus 7, 180 squared, minus 5. And there I have the vertex form of the equation. So again, unless we're told to derive the standard equation, let's use what we know about the key features of a parabola, the focus, the directrix, and the vertex, to create the vertex form of the equation. Should be a much quicker and easier concept. Now let's extend this concept a little bit into application problems. So with most things, we want to see how we can use this map. The parabola is extremely useful, mainly in 3-dimensional aspects, but we can take a look at a 2-dimensional version of a parabola and apply that to 3D scenarios. So in problem 4, it says the largest radio telescope in the world uses a 1,000-foot parabolic dish suspended in a valley in Arecibo, Puerto Rico. The antenna hangs above the vertex of the dish on cables stretching from 2 towers. The accompanying figure shows a cross-section of the parabolic dish and the towers. Assuming the vertex is at 0, 0, find the equation for the parabola. Find the distance from the vertex to the antenna located at the focus. So first thing that we want to do is find the equation that represents this parabolic dish that's shown there. Okay, so what it says is it's a 1,000-foot in diameter. A 1,000-foot dish here is represented by the diameter. We need to find the equation. Now that goes back to knowing the vertex form. It doesn't say standard, so let's use the vertex form of the equation. The vertex form of the equation is 1/4 d times x minus h quantity squared plus k. What this tells us is the vertex is at 0, 0. In most cases, we're going to put the vertex at 0, 0 unless we have to do something else with it. So I'm going to go ahead and substitute in 0, 0 for h and k. And now I have y equals 1/4 d times x squared. This was also an equation that we talked about in part 1 of the notes. We need to find the equation. That's the first thing And we need to find the distance from the vertex to the antenna located at the focus. So notice that in order to find the equation, I need to know D. D is actually the distance from the vertex to the antenna that's located at the focus. So to answer both questions, I need to know D. If we don't know where the focus is at, we might look for a directrix. This gives us no information about a directrix. So we need to find a way to come up with this equation or come up with the value for D without using a focus or without using a directrix. This is something we haven't done. What I may look at this equation and notice is that I have two other variables, an x variable and a y variable. That x and y represents any point along this parabolic dish. Taking a look at the graph, one of the things that or the picture here, one of the things that it shows us is that the dish is 1,000 feet across. We know that it's 1,000 feet across. We also know that the dish is 200 feet deep. So from the very top of the dish to the very bottom of the dish is 200 feet. So what I can do is I can strategically place a point here on the edge of this dish. The point, for this point right here, I can come up with the coordinates for. This point would be that distance to the right, that is shaded here in this bluish purple color, and that distance up. Well, we know that the vertex is at 0, 0, and this is symmetric on both sides. So to the right, we must move 500 feet. We can see there that it's labeled that we moved up 200 feet. So this point would be at the location 500, 200. This gives us an XY coordinate pair. Now, why is this useful? Well, if I go back to my equation, I can substitute in for y as 200. I can substitute in for x as 500, and I can use this to solve for d. So if I want to square 500 to simplify this equation, this would be 200 equal to 250,000 over 4d, and now I can solve for d. I can cross multiply, or multiply, sorry, in this case, I could cross multiply, but multiply by 4d here. So this would give me 8, not 8,000, it should be 800. This would give me 800d equal to 250,000 if I multiply again both sides by 4d. So I can do 250,000 divided by 800, and I can find out that d is 312.5. So the distance from the antenna to the vertex is 312.5 feet. So that's one of my equations. The other, or one of my answers, the other answer was to find the value of the equation. So now I can use this value d and substitute it back into my original equation. So y equals 1 over 4 times d. So 4 times 312.5, which is 1,250 or 1250 x squared. So now I have an equation to represent the parabolic dish, and I have the distance from the vertex to the antenna. So what this is useful for, if we know we have the dimensions of this canyon, or we know that we need a parabolic dish of this size, I can create my equation. That will give me a path to map out the creation of the parabolic dish. And then I can use that distance d to find out where to put the antenna so that all of the sound that comes in will reflect off of this parabolic dish and go directly to that antenna so it picks up all of the sound from outer space. So this is the same concept as the Newtonian telescope, just using radio waves. And here we use the vertex formula of the analytic parabola to answer both questions. Let's take a look at another example here, problem number 5. It said sound technicians at professional sports events often use parabolic receivers as they move along the sidelines. If a two-dimensional cross-section of the receiver is modeled by the equation y equals 1 over 54x squared and is 36 inches in diameter, how deep is the parabolic receiver? How far from the vertex of the parabolic receiver should the microphone be placed? So you guys, if you watch the NFL, you've probably seen these, especially now. You can hear them. They're like the big shields that the guys carry around, and they've got a little microphone sticking out of them, and they can hear everything from the field using those things. We're just dealing with a cross section of this. So notice that they gave us the equation y equals 1 over 54x squared. So I know that this is going to be a parabola that opens up because y is by itself, so it's vertical. It's going to have a vertex at 0, 0. And this is what I know about the parabola. So I can, just based on the equation, so I can go ahead and, if I wanted to, put it on some axes. This is really sketch kind of rough, but you get the idea. So now we also know that 1 over 54 is the leading coefficient of this parabola. So two things that they ask us to find here. They ask us to find the depth of the parabolic receiver, and they ask us to find where the microphone should be placed. Well, remember, all of the sound is going to come into this parabolic receiver and reflect off of it into a centralized location. And that's going to be what we call the focus. So we want the focus to be the location of the microphone. Now that focus needs to be a certain distance from the vertex. That distance we can represent as d. Remember from the equation that essentially the absolute value of a is equal to 1 over 4d. Well, we know what a is for this equation. It is 1 over 54. So 1 over 54 is equal to 1 over 4d. If I cross multiply, 4d equals 54. And then I can solve for d dividing by 4. So d equals 13.5. So how far from the vertex of the parabolic receiver should the microphone be placed? Microphone to vertex should equal 13.5, and make sure we have our units here, inches. Okay, you don't have to write complete sentences, but let's give some context. So microphone to the vertex is 13.5 inches. That's the first thing that we were able to find. Now, the second thing it says is how deep is the parabolic receiver? So we also want to know, basically, how far is it from the tip of the parabolic receiver down to the base of the parabolic receiver. So let's call this distance, let's just use a random variable, let's call it r. We need to find r. Well, r is not the same as d. You can see here in my rough sketch, but potentially this dish, the microphone could be further away than the edge of the dish. Potentially the edge of the dish could be higher than the microphone. We don't know. What we want to know is how deep this microphone is going to be. One of the things that we do know is the entire dish has a length or a width, a diameter of 36 inches. So let me place this point here, and I'm going to give this a capital R, and it's going to have coordinates. Oh, we do know what the x coordinate is. The x coordinate is going to be halfway across the dish, or the radius of the dish. It's going to be 18. We don't know what the y coordinate is. The y coordinate is r. But we can solve for this. We can substitute these values into the equation that was given to us to be able to solve for r. So r is equal to 1 over 54 times 18 inches quantity squared. And this we can do in our calculator. So 1 over 54 times 18 squared would equal 6. So the receiver is 6 inches deep. So here again, we're using the vertex form of the equation to get some different information about our parabola. This is a good place to stop. So this has completed everything that we need to know for Algebra 2 about the analytic parabola. When we reconvene in class, we'll have the opportunity to go over questions and to work on homework as we prepare for our upcoming quiz. As always, thank you guys for tuning in and have a good day. I'll see you soon.